In this video, we're going to apply our knowledge of quadratics to some of the more complicated extended response style questions. The first type of question are the families of functions style questions, where you're given a bunch of information and you have to solve the unknown coefficients of a quadratic. The second kind of question is where you're trying to solve the maximum or minimum of a certain quantity, usually area. And by the end of this video, you'll know how to approach both of these types of questions. For those who don't know me, my name is Chris Iannatoni. I used to work as an engineer for a defense company, and I've since left that to start a career in tutoring. I make these videos so that VCE students can do the best they can in math methods. With that out of the way, let's get into it. All families of functions questions will give you a bunch of information about a quadratic, and you'll be asked to figure out the rule of that quadratic. A big part of this is going to be to figure out what form of quadratic you should use. There are three choices. You could use the polynomial form of the quadratic, you could use the axis-intercept form, or you could use the turning point form. The polynomial form tends to be the hardest of the three to use, so where possible we choose to avoid that. Let's look at some examples. The first scenario is where we're told the turning point of our quadratic. Under these circumstances, the turning point form is going to be the most appropriate because we can use one piece of information to solve multiple unknowns. In this example, we have a turning point at 1, 3. That means that we have a shift to the right by 1 and a shift up by 3. The shift to the right by 1 is expressed by x minus 1, and the shift up by 3 is represented by a plus 3 at the end of our quadratic. All we have to do now is solve for a. A is always solved by subbing in an additional known point once you've solved all the other coefficients. In this case, that point is going to be 0, 4. So we sub it in and then solve for a, giving us a solution a equals 1. Having found all the coefficients, all we do now is put it all together. The second possibility is that you're given the x-intercepts of the function. Under this circumstance, it is best to use the axis-intercept form of the quadratic, since once again we can very quickly figure out a bunch of coefficients with the information that we have. If we have an x-intercept at -2, then that means that one of those terms must have been x plus 2. And if we have an x-intercept at 1, that means that one of the terms must have also been x minus 1. And once again, if we're trying to solve for a, then all we're going to do is sub in the additional known point. And finally, we're just going to put it all together. The worst case scenario is when you have 3 random points with no relation to each other. This is where you would have to do a 3-way simultaneous equation with the polynomial form. Starting with the point 0, 5, we're actually able to figure out what c is immediately. The remaining 2 points are going to form the 2 equations that we use to solve our simultaneous equation. I'm going to use the elimination method because I can see an easy way to cancel out one of the variables, but you can also use substitution if you prefer. Once you have all the solutions for a, b, and c, all you're going to do is sub those into the polynomial form, and that's your answer. These kinds of questions require you to find either the maximum or the minimum of a certain quantity. In the case of quadratics, this is usually something to do with area, and we solve these kinds of questions by using this framework. Let's run an example. So to begin with, we need to figure out the specific rule that we're dealing with. In this case, we're trying to find the maximum area, and so we need to start by figuring out what our area equation is. We're told that the garden is rectangular. That means that our area equation is going to start off with just being length times width. This gives us a good starting point. The only problem with this is that this uses 2 different variables, length and width. Ideally, we only want one variable in our equation, so that's what we're going to focus on next. In order to achieve that, we need a related equation. And this is going to come from the fact that the total amount of wire, the total perimeter of our shape, has to be 20 meters. The perimeter of any rectangle is just the sum of all of its edges. So our total perimeter of 20 meters is going to be 2 times L plus 2 times W. The reason this matters is because we can actually rearrange this equation to get one of the variables on its own. In this case, I'm going to choose width, but it honestly doesn't matter which one you get on its own. All we do from here is substitute that rearranged equation into our area equation. And when you do that, if you had rearranged for width, you're going to get your area equation purely in terms of length. If you had rearranged for length, it's going to be in terms of width, but that's besides the point. So to summarize, step 1 is all about finding your area equation purely in terms of one variable. In step 2, we're going to sketch our function. The reason why we do this is to make it easier to see where that maximum or minimum is. There is one important thing to consider here. A very common question is to ask what is the maximal domain of this area equation. This just means we need to figure out what are all the valid x values, or in this case length values, for our function. For any quadratic, this usually just means all real numbers, since quadratics are defined from -infinity all the way to +infinity. But this quadratic came from an extended response question, there are real-world limitations to what L could possibly be. What we have now is an area equation, where area is on the y-axis. In the real world, area can only be positive, so our graph must only therefore have positive y values. So it's going to cut out all the y values that are negative. If this isn't enough, then you can also consider the x values, or the length values, as well. In the real world, length can only be positive. So if there were any negative length values, then you could also chop those off as well. Okay, after handling all of that, we have our graph. Now we move on to step 3, which is identifying where the maximum or minimum is. In this case, we care about the maximum. Just by looking at the graph, we can see that the maximum is going to occur at a turning point. So the path forward is clear. We need to figure out that turning point. We have many methods to do this. The fastest way that I can come up with is to find the midpoint of your axes intercepts, giving you a midpoint of length equals 5, and then from there you're just going to plug that back into the area equation to get the corresponding area at length equals 5, giving you a total answer of 25 meters squared. Don't forget the unit. The reason why we harp on about including the unit is that you will genuinely just lose the mark if you don't include the unit. Sucks, but that's the game. The reason we cared so much about finding the domain is because the maximum of a function isn't necessarily guaranteed to be at a turning point. Let's see what happens when it isn't. This is actually the same example as earlier, but now it has an additional restriction on the length. It cannot exceed 4 meters. To start with, we handle it the same way that we handled the previous question. We start by finding the area equation, purely in terms of one variable, and then we sketch that function. This is where it differs a little bit. The sketch of this function must now be truncated a little bit. We're no longer sketching from 0 to 10, because now our length cannot be greater than 4. So we're just going to chop that graph off at L equals 4. And when we do that, we see that the turning point is no longer included in that domain. So to find the maximum of this graph, we can identify that the maximum is going to occur when L equals 4, since that's where the tallest y value is now. So just like before, we're going to sub in L equals 4 into our equation, and then solve for the new area, giving us an area of 24 meters squared. If you found this video helpful, then you should consider joining my free community. I host a Q&A call every week to personally help you through any of your specific questions, and you'll also get access to more resources like this, including written and recorded lecture content, as well as practice exams and SACs with detailed solutions. It's pretty cool, you should check it out. I'll see you there.